Hi, during this session I'm going to explain kinematic graphs. So these are graphs which show distance or displacement against time, velocity against time, or acceleration against time, and how they can be really useful in explaining or extracting information about a journey. I'm going to do that by going through an example with you. So I'm going to introduce you to a journey now. This journey involves a small car. The small car starts from a distance of 0 and it slowly starts to accelerate away. Okay, it accelerates away until it reaches a constant velocity. So here we can see the constant velocity it finally reaches is 30 meters per second. It carries on travelling at this constant velocity. And then after a certain period of time, so when we reach what I think it was going to be 40 seconds, we'll see it to start to slow down again at 35 seconds. So it's going to slow back down again until it finally reaches and comes to a halt. So this is the journey which I'm going to show you as a distance time and a velocity time graph, and we use that as an example to think about what these. So what we have in front of you is the distance or displacement time graph for that journey we saw. Now there's some features which are important here. We've got my distance on the y-axis and the x-axis along the bottom we've got time in seconds. Now features which we're going to try and emphasize from here that are really important. Now the car is starting to move, and we can show that the speed is changing, and that changing speed is shown by an upward curve on the graph. When the car is going at a constant speed, what we have is we'll end up having a straight line. So that shows that the gradient is related to a constant speed, or the speed. As the car curve begins to curve downwards, that's an indication that the car is slowing down. And finally, when the line is flat and horizontal, it means that the car is not moving, as there's no change in displacement. So that means the speed has to be 0. Key points here: if we think about the constant speed area, what we can do is we can work out the gradient for that period. Here the car's travelled from 200 to 800 meters during a time of, or taking a time of 20 seconds. That means we can calculate that the speed during this period was 30 meters per second. So that's quite useful. This is a velocity time graph. So here we can see exactly the same journey. We can see that my car is increased its velocity up to about 30 meters per second. It stayed at that constant velocity for a set period of time, and then slowed back down again, coming to a halt where it was stationary for the last 5 seconds of this. So let's look at what we can extract from a velocity time graph. If we see that there is a gradient, it means that if the gradient is upwards, the speed is increasing. It's horizontal, which means it's a constant speed and acceleration is 0. And if we see a downward gradient, that means that the car is deaccelerating. And obviously, if the line is horizontal along 0, that means there is no speed at all and the car is stationary. Now what we can do is that we can work out the area under the graph is equal to the displacement. The total area is in fact going to be 10,050 meters. Oh, 1,050 meters. Now the way we do this is we break it into sections. First of all, we form a triangle here. So the area of this triangle is going to be 15 multiplied by 30, which is the height, divided by 2. Now this triangle is also exactly the same as this triangle over here. So we have 15 seconds on the bottom, gives a height of 30 divided by 2. And that gives me a value of 225. With those two triangles, I add them up, and then I add the area of this rectangle. So this is from 15 to 35, so that has 20 seconds along the bottom and a height of 30, and that gives me a height of 600. So my final total area is 1050 meters. Now you may remember that that's not the value which was given to us on the dashboard or shown on our distance time graph. Now the reason for that is that this is not a perfect triangle. We can see that there's a slight curve in that line there, and that's something for us to think about. Often when we make simplifications, we'll find that our values won't quite be perfect. So that's something just to be aware of. Now let's compare these two journeys and see how they both graphs tell the same story. The speed is increasing, so that means that here there's a positive gradient on the velocity time graph, and on the distance time graph or displacement time graph we'll see that it's curving upwards. In both sections we see that there's a constant speed of 30 meters per second, so this is a horizontal line in the speed time velocity time graph, and a constant gradient in the distance time graph. And we can see in both phases there's the decreasing of speed. There's a downward curve in the distance time graph and just a reduction in speed overall on the speed time graph. And finally we get to the end when the speed is 0, and we can identify that from both graphs. So key points here: gradients of graphs. Gradient of a displacement time graph is the velocity. The gradient of a velocity time graph is the acceleration. It can be either instantaneous or average depending on what you calculate. The areas underneath the graph, they can be calculated by creating geometric shapes. The area underneath a velocity time graph is the displacement. I haven't shown it, but the area underneath an acceleration time graph is the velocity. Let's think about a bouncing ball now. So here's my ball. I've made it bounce up and down. Think about how you'd graph this situation. What we can see is I've got position time, velocity time, acceleration time graphs for each one of these. Position time, you see the ball falling down, hitting the ground, bouncing up and down. Not gaining to the same height again, some energy has been lost, bouncing up again and coming back down to the ground again. The velocity we can see is, as it's falling down, it's in a negative direction, and then just as it reaches the ground, it's going up again, so we have a positive direction, and it falls down at a constant velocity, hits the ground, and then changes its direction, going up again, and onward and onward. The key bit of acceleration here is we can see that the acceleration is always, or generally, minus 9.81 due to gravity, but it springs up and goes in the other direction at the point when it's in contact with the ground as it changes direction. Think about what the curves would be like for a ball thrown upwards. Displacement would show it would curve upwards, reaching the highest point and then come back down again. At its highest point the slope would be 0. It could be considered to be momentarily stationary. That point of momentarily stationary is the point where the velocity goes from being in the upwards direction to the downwards direction, so from positive to negative here. We can see that the velocity, assuming it's not being slowed down in any way, is going to find the velocity time graph. What we see is a constant gradient, and that gradient is caused by the acceleration or deacceleration or acceleration due to gravity. So that's why we have a constant gradient all the time, and that's shown effectively by the fact that if if we look at the acceleration time graph, we have a constant negative acceleration, which is caused by gravity slowing it down. Hopefully that gives you an overview of everything you need to know about kinematic graphs.